Okay, so we're trying to make connections between derivatives and integrals. Okay, so Unit 8 is all about making connections between derivatives and integrals. So if we think back to average velocity, okay, on a certain interval, so maybe from A to B, right? That's usually our interval that we're talking about, a lower bound of A and an upper bound of B. Okay, average velocity or average rate of change, right? Also known as slope. So if we had a graph, say, and this was our graph, and this is your lower bound of A and your upper bound of B. Okay, then the average rate of change would be the slope of the line that connects these 2 points, right? This is the slope. So average velocity. Remember, velocity is the derivative of what? Position. So velocity is the derivative of position, right? Position, derivative of position. So if this was our position graph and we're looking for the average velocity between A and B, we would take the y value or the position at point B, and we would subtract the y value or position at point A and divide by B minus A, the x values, right? So this is basically slope, right? It's y minus y over x minus x. Average velocity, average value is a slope problem. Okay, so we take the y value at the end, we subtract the y value at the beginning, and we take the x value at the end and subtract the x value at the beginning. So specifically for velocity, those points come from your position function, because velocity is a derivative of position. Now, what about average acceleration? What does acceleration relate to? Acceleration is the derivative of the velocity. So then average acceleration is the velocity at point B minus the velocity at point A. So we're still talking about the closed interval from A to B, divided by B minus A. Okay, so if we're asked for average acceleration, those values come from your velocity function. And if we're asked for velocity, those values come from your position function, because the velocity is the derivative of position and acceleration is the derivative of velocity. So let's put that together with what we know about the fundamental theorem. Okay, so if we have some fundamental theorem A, right, where A is the velocity, or rather the acceleration, and we're going to take the integral of acceleration. Okay, when we take an integral, what do we find for our function? The antiderivative. When we take an integral, we're finding the antiderivative. So what is the antiderivative of acceleration?
Velocity.
Velocity. So this would be the velocity evaluated at point B minus the velocity evaluated at point A, right? Because velocity is the antiderivative of acceleration. And when we're taking an integral, we take the antiderivative of acceleration, which is velocity, evaluated at point B, and then subtracted the evaluation at point A. And we're still multiplying all this by 1 over B minus A. So if we do some type of a simplification, right, so we have all of that divided by, basically we have V of B minus V of A divided by B minus A. Okay, what did we just say that was? Average acceleration. Okay, so the integral of an acceleration function is simply the average acceleration on that interval. Okay, that's exactly what we had just showed a second ago, is average acceleration is V of B minus V of A divided by B minus A. And that's exactly what you get when we have 1 over B minus A times the integral of acceleration. And we'll find a very similar thing here, because V of t stands for velocity. So what is the antiderivative of velocity? Position. So this would be 1 over B minus A times the position function evaluated at B minus the position function evaluated at A, because position is the antiderivative of velocity. Okay, we just said this was known as average velocity. Okay, so in other words, average velocity is the rate of change of acceleration. How fast is your velocity changing? Okay, average acceleration is the rate of change of your velocity, and average velocity is the rate of change of your position. So we're making connections between the integral and the average rate, okay, which is why these are all average value problems. So in general, if we want to find the average value of a function on a closed interval, okay, that would be the interval from A to B. That is the function evaluated at B minus the function evaluated at A over B minus A. Okay, so that is the average value of a function on a closed interval. So our next question says find the average value, right? Average value, so you want to think about integrals from 1 to 3. So 1 is your A value and 3 is your B value. So we can write down the equation, integral from 1 to 3. 1 over 3 minus 1, right? Don't forget about that 1 over B minus A part. 1 over B minus A times the integral of x cubed root sine squared x dx. Okay, now we're going to do this in our calculator. So let's try and input that into your calculator and see what you get. So 5.848 when you round to 3 decimals. Okay, AP wants you to round to 3 decimal places. Okay, so the next one says average value from 2 to 6. So A is B, or A is 2, and B is 6. So 1 over 6 minus 2 times the integral from 2 to 6, 2 minus 4x dx. Okay, and if you put that into your calculator correctly, you should get negative 14. Negative 14. Okay, so let's go to the second page. Hang on, let me take a picture. I'll be right back. So this is a problem about snow on a mountain somewhere. Okay, so we have some snow that is accumulating, right? We have the accumulation of snow with S, and we have the melting of snow with M. Okay, so snow is being added at the same time some snow is melting. So our first question says, what is the total volume of snow added? So just our snow added over the first 6 hours. So this is an accumulation problem, aka an interval from 0 to 6. Right, so those are the first 6 hours from 0 to 6 of our function for snow added, 24 minus t times the sine squared of t over 14. dt, right? So we are adding snow. We want to know the total volume that has been added. So we're going to take the integral of our adding function, the snow added function, from 0 to 6. So you're going to put that right into your calculator, right? There's no way that you're going to want to do this without a calculator. It would be murder. So let's put that in our calculator. We'll be right back. So 142.413 cubic yards of snow has been added in the first 6 hours.
Decent amount.
Decent amount of snow. So the next one says find 0 to 6 of M and 1/6 of 0 to 6 of M. So this is going to go right into your calculator. 0/6 of 10 plus 8 cosine t over 3 dt. Okay, all this goes directly into your calculator, and we will find an answer of 81.823 cubic yards. Okay, and then if we do the other one, 1/6 of this, which is basically the same thing. Okay, this comes out to be 13.637. Okay, and since it's 1/6, remember this is the average rate of change, so that means it's yards cubic per hour. Okay, so the first one is just talking about the total amount, right? So if we're going from 0 to 6 of m, that's the melting. So the first one from 0 to 6 is the total amount of snow that has melted. Okay, total amount melted from t equals 0 to t equals 6. Okay, if we're just finding an integral, that's the total amount, right? That's the accumulation, the sum of all the little rectangles that we've added up. So there are 81.823 cubic yards that have melted in the first 6 hours. Okay, but the second one, when you do the 1/6, now we're talking about the average rates of snow melting. Okay, now we're talking about an average rate, an average value. Whenever we do that 1/6, you take the total amount and divide it by however the time was, right? We're dividing it by hours. That's giving you a per hour or a per minute or a per second rate. The average rate of snow melting from t equals 0 to t equals 6. Okay, so there's a rate, which is your rate of change of melting, and then there is the total amount. Okay, so if you have this divided by 6 business, where we're splitting into every hour or every minute, that's an average rate, where the first one is just an accumulation. Okay, part C, is the volume of snow increasing or is it decreasing? Okay, so here we're going to go back to a little bit of something from a previous unit. And remember, if we had a function f, what could we say if its slope was positive, right? What if the first derivative was positive? That means our function f is increasing, right? If the first derivative is positive, our function is increasing. And if your first derivative is negative, that meant that f was decreasing on that interval. So that's what we're going to do, is we're going to take the derivative of our snow amount function. Okay, the derivative of your snow amount function, and evaluate it at 4 to see if that number is positive or negative. Okay, so let's talk about what that equation looks like. So the amount of snow at any given time t, right? So A stands for amount, or V for volume if you want to do V.
Oh, sorry.
Okay? It starts with our initial quantity. So we started with 50 cubic yards of snow, right? That's how much we started with. And then we are adding, right? We're adding some amount of snow from 0 to t, right? We're adding some interval of snow, some volume, some accumulation. And we're now subtracting some other accumulation by melting. Okay, so we're adding some snow and we are melting some snow. That's t on top of the integral. Yes, both of these integrals have a t on top. So this is in general. Our amount in general is found by doing this integral of adding snow and the integral of subtracting snow. Okay, so let's take the derivative of this amount of snow function. A prime So what is the derivative of a constant? Nothing, right? So that one doesn't give us anything. What is the derivative of an interval? The derivative of an interval. Okay, so we might have to go back to the second fundamental theorem of calculus. Okay, so the fundamental theorem said, right, if we have a function defined from 0 to another variable, right, of your function, then the derivative is found by plopping this one into there, right? We plop it in. We take the composition and we multiply it by g prime, right? The derivative of that upper limit. So if your upper limit is a function, right, then the derivative of that integral, right? We're taking the derivative of an integral by doing some composition, multiplying it by the derivative. So what's going to happen when we do that here? We're going to take our limit of integration and plop it in, and then multiply it by the derivative. So what's the derivative of t? It's just 1. So the derivative of our integral is just the addition evaluated at any given time. Right? That is the rate of change of your adding snow function. So we're going to do a similar thing with our melting snow function. Right? We want m prime, so we're going to take our limit of integration and plug it into your function, and then multiply it by its derivatives. In other words, just m of t. So the amount or the rate, right? The volume, we're gonna see if this number is positive or negative. Right? That's what we're trying to decide here. If it's positive, then your volume is increasing. If it's negative, then your volume is decreasing. So let's see what we have. Your s function was 24 minus 4 times the sine squared of 4 over 14. Okay, that's what your s function was, your adding snow function, evaluated when t equals 4. And we're going to do the same thing for our melting snow function, 10 plus 8 cosines of 4 over 3. Okay, so we're going to put both of these into your calculator directly as you see them. We're not putting an integral in the calculator. We're just putting in a function with those exact numbers. Okay, and when we do that, we get 11.8004 as your answer. Okay, which is fantastic. But the best part is that it happens to be a positive number, which means the volume of snow is increasing. So we're getting more snow on our ski slopes, which is good for skiers. So the volume of snow is increasing at t equals 4. Okay, so we have to be specific to say when it is increasing at t equals 4. Because your derivative of your snow amount is positive, the volume of snow is increasing. Okay, so that's a pretty good question. Being able to take the derivative of an integral. Remember, you plug in that upper limit of integration and you multiply by its derivative. Okay, there are much harder ways to do it, but that is the easier way. Okay, part D, how much snow is on the slope after 5 hours? So we're going to go back to our A function, your amount. Your amount after 5 hours was your 50 plus the integral from 0 to 5 of your additional of snow minus the integral from 0 to 5 of your melting snow. Okay, and of course, this is going to be done all in your calculator, so make sure you still have these values in there. Just change the upper limits to 5, and it's a pretty easy thing to do. And you should be getting a total of 95.335 cubic yards of snow after 5 hours. Okay, so hopefully you have a calculator that is smart enough to do that for you and with you. Okay, the last question says, suppose the machine is turned off after 10 hours. Write an equation that could be solved to find for K when all the snow would be melted. So we first have to find the amount of snow at 10 hours. So we're going to do the same thing we did before, but now change all of your upper limits of integration to 10. And when you do that, we get a snow volume of 183.193 cubic yards. Okay, so the same calculation you did in part C, only now with an upper limit of 10. So then if we take that amount of snow, right, this is just the snow we have, and we subtract the melting, right, we want all of our snow to melt. From 0 to I don't know when, right, we want the K value. How long do we have to wait until all of the snow melts, until the snow equals 0? All right, so this would be the equation that you would want to potentially solve for K, right? Because K is your upper limit or your time. How long do we have to wait until all the snow is gone, until snow level equals 0? And that's your equation. Okay, so we have a direct correlation between derivatives, right? Antiderivatives, velocity, acceleration, position, and integrals. Okay, average value. If it doesn't say average value, then you're not doing the 1 over b minus a part. You're just doing the accumulation. But if it does say average value, then you add in that 1 over b minus a. Hopefully this helps you a lot. Goodbye.